Concept is a new element of C++. It was introduced or will be introduced in C++20, but the actual idea of concepts goes back a really long way. The original work was done a long time ago by Alexander Stepanov and actually goes right back to the very earliest days of C++, one could argue. A good example here, Stepanov in his book, Elements of Programming, this is from 2009, he actually mentions the idea of concepts all the way back in 2009, and they probably predate that as well. But they are very new to C++. So what we're going to have a look at this morning is the basic syntax and semantics of concepts and how they relate to how we use templates going forward in C++. I'm cognizant here that not everyone is fully conversant with templates. So what I want to do to put concept into some sort of context is to have a brief run through of template code in C++, some of the more relevant elements. I want to look at the idea behind type inference and type deduction in template code. I also want to have a look at some of the features that are already available in C++, like SFINAE here, substitution failure is not an error. And we're going to use those as a lead-in to the idea of requirements on templates and then ultimately onto concepts themselves. What I'm not going to be doing here is making any kind of value judgments on concept. This is a potentially game-changing way of looking at generic code in C++. Could really change the way we think about things. But there are going to be a lot of people spending a lot of time looking at a lot of the subtleties of these things going forward. So at the moment, all we can do is look at syntax and semantics, and hopefully put you in a better place going forward to take part in the discussions. I'll start right at the beginning then by looking at basic function templates and the idea of type inference and type deduction. So let's start with that as a basic concept. The idea behind function templates or templates in general or generic code in general really could be summed up to quite simple. Don't repeat yourself. As programmers, when we look at our code, we realize that actually sometimes the algorithms that we are writing are the same, and the only thing that changes is the types that those algorithms operate on. We can take this idea and make the algorithm a generic thing and use templates to specify different types for different versions of this function. So what we have on our screen at the moment here is a very, very simple function template. It finds the minimum of 2 values. We specified that when the function template itself doesn't specify the actual type of the parameters, that's specified by a placeholder. We've called it t, as is the traditional way. In our main function here, you can see that we are creating instances of that template function. That is, we are telling the compiler to actually use the function template to generate new code where we are substituting the template parameter t with either int or double. Now that's useful, I guess, very powerful, but actually the real power comes in when we let the compiler do a lot of the work. But before we do that, let's have a look at what's going on here. When I'm creating an instance of a function template, what the compiler is actually doing here is it is looking for a function declaration up front. If it cannot find a normal function declaration, we are telling it to look at the template itself, the function definition here acting as a declaration as well, and we are saying create a call to this function min int. Of course, At that point, the compiler may or may not have a body to that function, so the compiler will normally go away and generate a body to that function where it will substitute the template parameter t with the supplied argument int, and we'll get a version of that function, int min, where two parameters are both ints. Similarly, if we supply a double as the template parameter, the compiler can generate a new piece of code from that. That's the basics of function template instantiation. I'm glossing over it and making it somewhat more superficial than it needs to be for the moment, but that's the basic principle to get us going. Where it starts to become really powerful is we can defer a lot of the work to the compiler. That is, the compiler can look at the arguments to the function and it can deduce, it can infer the function declaration from the types of the arguments here. One thing, in this particular case, the compiler needs to be able to make an unambiguous inference of the type. So if we look at our third call here, which is marked as an error, one of the arguments is an integer, one is a floating point, a double specifically. The compiler has to work out here, well, if I supply the value 10, it can deduce that the template parameter t is an integer. If I supply the value 20.9, it can infer that the type of t is a double. Well, it cannot be both an integer and a double. At that point, the compiler will have to give up and say, I'm sorry, I can't infer what the type of that parameter is. Of course, I can explicitly state what the template parameter is at the bottom there. There's no inference going on at all. And sometimes that may be a necessary thing for us. Notice in this particular case, we have explicitly specified that the template parameter is type int. So the function declaration here determines that the template parameter t is an integer. However, when we call the function, the double, the second double, 20.9, will be converted to an integer on the call to the function, which may or may not be what we want. Of course, we can have as many template parameters as we want on a template function, and the compiler applies the same set of rules to each template parameter in turn. Notice in this particular case, the first call to the function min has a double followed by an integer, so we get a version of the function declaration which is min double and int. In the second case, we get min int and double, two completely separate function declarations. It's probably worth spending just a little bit of time looking at the rules that the compiler uses. It actually uses the same rules as automatic type deduction. That's where automatic type deduction gets its logic from. It's the same mechanism as templates. The idea is we use the argument type on the call to the function to deduce what the template parameter is. Now, there are a set of rules that the compiler applies in order to work that out, and I'll look at those in a moment. CV const volatile qualifiers are always applied after type deduction in this particular case. And something that we're going to exploit a little bit later. If via the process of template type inference, we generate an illegal function declaration, the compiler will silently ignore that. This is what is known as substitution failure is not an error, and we are actually going to exploit that later on. And of course, that function still has to be parsed as correct code after the type deduction takes place. So we still have to have something that would be compilable code. So let's have a look at some of these rules. Let's start simple. The simplest possible case we can have is a template parameter, creatively called func here, with a single template parameter, which is a pass by value parameter, just a plain old type T. In such cases, the compiler will ignore any CV qualifiers or any references applied to any of the arguments. It will basically decay to the raw underlying type. So in this case, whether I pass in a reference to a value, an R-value expression, a plain literal here, or even a reference, the CV qualifiers will be stripped off, any references will be stripped off, and the underlying type will be used. There's one special case here I've shown, second from bottom. If I'm passing a C-style array here, if I'm using the array name in this particular case as an L-value expression, that will decay to a pointer. So the compiler will pass that as a pointer to whatever type is in the array. That's not unreasonable. That's how C-style arrays are passed quotes by value in C++ anyway. So the template deduction rules follow that logic. If I want to CV qualify the template type, that CV qualification happens after the type deduction. So once again, any CV qualifiers are stripped off, any references are stripped away, and then after the type has been deduced, the CV qualifiers will be reapplied. Notice in this particular case, the CV qualifier is applied to the pointer type if I pass by array. So it becomes a constant pointer to an integer, not a pointer to a constant integer. Stylistically, this is why I nearly always put the CV qualifiers for template parameters after the type name to give some clue that that's what's going on. If I'm passing by reference, specifically L-value reference here, the rules have to change. In this case, if I'm creating a function that takes a reference, I cannot ignore CV qualifiers. The easiest way to think about this is if I ignored CV qualifiers, it would allow me to have a reference to a non-constant type being referring to a constant object. And we can't do that. We can never be less restrictive with our references. So CV qualifiers can't be ignored in this particular case. When it comes to R-value references, the rules change again. And something about these rules, I'm sure there is a lot of thought and logic gone into them, but to me, it always feels like they started with the answer and worked backwards to the beginning. So let's take these examples here. I have a template function called func, and it takes an R-value reference as a parameter. If I call that template function or function template with an L-value expression, the compiler will deduce that the template parameter type is a reference to whatever the argument is. So in this case, it will be an L-value reference to an integer. If, on the other hand, I pass an R-value expression, in this case a literal, a pure R-value, I will get the template parameter deduced as just the raw underlying type. Okay, let's substitute those in to the function declarations. In the first case then, I will get an R-value reference to an L-value reference. In the second case, I will get an R-value reference to an integer. Now, ordinarily, that first example would fail because that's an invalid function signature. However, a new set of rules kicks in at this point. These are known as the reference collapsing rules. The reference collapsing rules say, if I have an L-value reference to an L-value reference, that will collapse to an L-value reference. In fact, any reference to an L-value reference will collapse to an L-value reference. In fact, pretty much everything collapses to an L-value reference except one specific case. An R-value reference to an R-value reference collapses to an R-value reference. If I apply this second set of rules to my function declarations, I get the following. I get two versions of func. The first version of func, if I pass an L-value expression, I get an L-value overload to the function. If I pass an R-value argument, I get an R-value overload to the function. This is what Scott Myers called originally his universal reference. That is, L-value expressions bind against L-value references, R-value expressions bind against R-value references. These days, it's more commonly known as the forwarding reference idiom. So we have this complete set of rules for type deduction. We can now exploit that and use that. I won't use it just yet, but we are going to use it later on. And we're going to have a look at some of the potential pitfalls that we get with generic code. The thing with generic code is it isn't completely generic. It always puts some sort of requirement on the template parameter. Let's take an example here. I have my min function from earlier. It just finds the minimum of 2 values. That will work for all of the scalar types in the language, the built-in types. But here I have some abstract data type, my ADT type here. If I try and find the minimum of 2 abstract data types here, I'm going to get an error. The error, unfortunately, is going to be deep inside the template code, and it's going to say that the type T must support the less than operator. My ADT type doesn't support it. In order to use that, then I'm going to have to provide my own implementation of the operator less than for my ADT type. So there is now a requirement on this function template. I can only call this function if I support that particular operator overload. If I don't support it, I can't call it. What's worse, and probably the horrible bit about templates, is the error will occur inside the body of the min function. And this is where templates get a lot of their reputation for nastiness from. It's not that the templates are particularly difficult to write. It's not that they're particularly difficult to use. But when they go wrong, you tend to get hit with a tsunami of word salad, which is really tricky to debug. It takes experience and skill. It tends to put a lot of beginning programmers off. So is there anything we can do to make this better? Well, let's have a look at it. Oops, there's a lovely typo on this slide. I do apologize. That should just say return, not CC return. Here's an interesting version. I'm comparing 2 string literals here. It says, what will be displayed? It might be hello. It might be world. I don't know. The one thing I can guarantee in this particular case is it is not going to do a lexicographical comparison of those 2 words. What it's actually going to do is compare their addresses in memory, because it's going to deduce that the type of that template parameter is in fact a pointer to a character, or pointer to a constant character in this particular case. So it's going to be comparing the addresses of those 2 strings in memory. This is not necessarily what I want. I've now got a semantic problem. Perhaps I could fix it by overloading the template function. I now have 2 versions of the min function, one that takes raw T types and one that takes pointers to T. In this particular case then, both of those template functions are potentially viable candidates. So the compiler actually has a set of rules here that says it will find the best match. In this particular case, as it deduces the type of the template parameter as a pointer to a constant character, it will determine that the second version of the function, the T star version, is the best match. And now it's going to compare the first 2 letters of the string. Better, I guess, but still not a lexicographical comparison. Our best option in this particular case is to overload with a non-template function. In this particular case, we have a non-template version of min that actually explicitly compares string literals using a string comparison function. In this particular case, if the compiler is doing type deduction and it finds a template version of the function and a non-template version of the function, the compiler will always prefer the non-template version of that function. So in our first example, the non-template version will always be preferred. Of course, if I completely ignore type inference and explicitly specify that I want to use the template version of the function, it will compare the addresses, which may or may not be what I want. Probably not in this particular case. So is there anything I can do to make this a little bit more palatable? Well, one of the options we've got is to actually disable functions if our requirements are not met. That is, if the argument we are supplying does not provide the facilities we need, we will disable the template function for that type. Let me show you an example of this. We're going to exploit what is known as substitution failure is not an error. Now, this is a technique that has been used in C++ for many, many years, but it's a nice lead-in to the idea of requirements. So it's a very, very simple function here, again, called do stuff, why not? And for reasons that I can't come up with off the top of my head, we are going to create a vector of some template type T, and we're going to insert elements into that vector by copying them, because this is an example. From my client code, I've got two types here. I have a movable type. Our movable type allows moving, but does not allow copying. It is a non-copyable type. Underneath it, we have a copyable type. It can be copied. Let's have a look at what happens when I call that template function. So I create myself a copyable object and call doStuff. The compiler will determine that the function declaration, the template type parameter, is of type type copyable in this particular case, and it can call that function. In the second case, the type inference says that the version of doStuff that will be called, it will deduce that the template parameter in this case is a movable object. In this case, the call is okay, but when it actually tries to compile the body of the function, I will get this wonderful error on the screen. Anyone who's done anything with templates will know that this is common practice. Rule of thumb, always read the first line and the last line of the error message. That will give you a clue. In our case, there is a clue at the bottom there. It says that movable's copy constructor is deleted. Use of deleted function, movable, const movable reference. Yeah. However, if you are not used to debugging template code, this can be frighteningly off-putting. And by the way, this is a subset of the error that was generated from this code. It would be much nicer if I could actually put the error at the point of call, rather than deep down inside what is in this particular case, the pushback function on the vector. Most of that error is coming from code that I did not write. So if I can push the error back to the client code, that will make my life, well, certainly my debugging life, a lot easier. One of the ways I could attempt to do this is by exploiting this substitution failure is not an error. That is, if I can get the compiler through type deduction to generate an invalid function declaration, it will silently ignore it. If there is no function declaration, then I cannot call the function. I cannot make a call. What will therefore happen is the compiler will emit an error in my code saying, I'm sorry, there is no function to call. There are three ways I can generate an invalid function declaration. First, I could have invalid function parameters. Secondly, I could generate an invalid return type. Or thirdly, and the one I'm going to exploit in this example, I could generate invalid template parameters, and that's the one I'm going to exploit here. So what I'm going to do is force the compiler for certain conditions to generate an invalid function declaration of that template function. So therefore, it will say, I'm sorry, I cannot find a function of that signature. What I'm going to use is something that is built into the standard library called enableIf. EnableIf is a template class, or a pair of template classes that exploits template specialization. The enable if structure here has two declarations. The first one, if you create an instance of this enable if structure with a Boolean value of true, it will actually declare a type parameter here, an internal type, which will be whatever your parameter will be. In this case, I've said that it will return the declaration of type as an integer. However, if I generate a version of the enable if structure where the first template parameter is false, there will be no declaration for the alias type, and I will get an error. I can't print out the type because it's not actually specified on that template structure. So what I've got now is a mechanism where I can either generate valid C++ code or invalid C++ code. This is what I'm going to exploit. What I also need is some mechanism at compile time of determining the truth or falseness of that enable if statement. In this particular case, I'm going to use something called a type trait. A type trait is a property of a type that can either evaluate to true or false, dependent on whether the class or the type supports the facility I'm looking for. In this particular case, I'm looking for the property that the type supports a copy constructor. So in the case of a copyable type, the isCopyConstructible value will come back as true. In the case of a movable type, the isCopyConstructible will come back as false. So I now have a mechanism for enabling truth or falseness based on some characteristic of a template type. Let's bolt all these together. There's a lot of horrible, ugly code on that screen now. What I've done is I've added an extra template parameter onto my doStuff function, and that second template parameter is going to be used to generate either a valid or an invalid function declaration, depending on whether the type T can support copying or not. Let's just break that down into a bit more detail. First of all, the way I'm going to do it is I'm going to generate an unnamed template parameter. That's what the type name part is. The reason it's unnamed is because I'm never ever going to refer to it inside the body of the function. But I can't just have an unnamed template parameter because the compiler will never be able to deduce what its type is. So I'm going to tell the compiler, if I don't specify what the template parameter is, default it. In this case, I'm going to default it to the Boolean true. It could be false, it doesn't matter. In order to generate the template type, I'm going to use the enable if from previously. In order to turn on or off the type on the enable if, I'm going to use a type trait. So there's my full construction. What does this mean if I bolt all of these things together? It means that if I have a copyable type and I call doStuff, if I substitute in the copyable type into this template parameter, we know that isCopyConstructible is false for movable types. So therefore, I will get a function declaration, a function signature that looks like the following: type name equals true. This is an invalid signature. This is not allowed. The compiler will silently ignore this. Substitution failure is not an error. However, if I supply a copyable type, the isCopyConstructible evaluates to true, which therefore means I get a function signature at compile time that looks like this: type name bool equals true. That is an irrelevant but syntactically correct function declaration. The compiler will allow this. So what I have now is a way of disabling the doStuff function for movable types, or more specifically, enabling the doStuff function for copyable types. Let's do that. I've put the term simplifying in quotes there. I'm not sure this is any more readable than the previous version. The compiler does provide some aliases to simplify the code somewhat, but it's still not pleasant to read. Once you're used to it, it is manageable, and there are some other games you can play to make this code more readable. But in general, this is the sort of code that tends to upset newcomers to C++. This is where requirements come in. Requirements are a mechanism that can now be applied to templates that allow us at compile time to determine characteristics of template arguments as part of type deduction and then generate errors at compile time if we fail to meet those requirements. So let's have a look at that. Here's a very simple example. It's a simple template class. It's a simple first in, first out fixed size buffer. This is nowhere near production code. It's a demonstration in this particular case. I can create instances of that class for integers and doubles, no trouble at all. However, if I want to use some user-defined type, in this case I have my abstract data type ADT, this is going to cause me a problem. The error it generates is not necessarily going to be very readable in this case. The ellipses at the end there shows that this goes on a lot. It repeats at least another 14 times. What is it trying to tell me? Well, it's actually trying to tell me in this particular case that my abstract data type doesn't support default construction. Yeah, obvious from the error message in this particular case. It would be really nice if I could actually have the compiler say, I'm sorry, you cannot use your ADT type in the buffer because it does not support copy construction, or doesn't support default construction, sorry. This is where requirements come in. Requirements give us a mechanism to do that. Let's apply a mechanism, a requirement to our template then. Here we go. I'm going to use another type trait. The requires keyword requires there a Boolean expression that is known at compile time. It must evaluate to either true or false. If it evaluates to true, then the template can be instantiated. If it evaluates to false, compilation will stop. In this particular case, the requirement that we've got is that the type T be default constructible. If I apply that to my code, as before, now I get the error that we can see in our terminal. It says, sorry, there is a template constraint failure in your code here. It says the constraint is not satisfied. That is, your ADT type is not default constructible. I'm not sure about you, but that is a lot more palatable as an error message. So one of the real advantages of concepts and requirements in templates is they make user code much easier to debug. The error is now pushed to your client code and not deep down inside the body of the template. We can extend this example a little bit further. Let's have a look inside the body of the buffer code, and you'll notice that for reasons, and yeah, in this case, this is not production code. There are far better ways I can do this, that I'm inserting and extracting the data by copy. Yes. That means in order to use this type, not only do I need to be default constructible, I also need to support copying as well. I need to support copy assignment, and I also need to support copying in general. Yeah. If for some very good reason my abstract data type isn't copyable, it would be nice if I could know that at point of instantiation and not deep down inside someone else's template code. So I can do that. Now in this particular case, when I get an error, the error comes up, and you'll notice it comes up inside the buffer push and of course buffer pop methods as well. This error occurs deep down inside someone else's code. A better mechanism then is to exploit requirements again. I can add additional requirements to my code. Here we go. I'm going to combine them together with Boolean logic. This template requires default construction. It also requires copy assignability. It also requires copy construction. Now, in reality, that could be type traits, as I've shown here. It could be certain type aliases that your type must define. It could be member functions that are required. It could also be member attributes. It could be any combination of those things that's in there. The problem with specifying the requirements like this is that it can get quite onerous quite quickly, and you could end up repeating yourself quite a lot. And this is where the idea of the concept comes in. A concept defines, if you like, a set of constraints or a set of required semantics for a particular type. Now, I'll admit right up front here, I'm following an example through. The concept of bufferable is not a good concept in reality, but let's just roll with it from a syntactic point of view. What I've done is I've taken a set of requirements, in this particular case, and I've given them a name. Notice the type of the concept is of type bool. That's a syntactic nod to types of other functions as well. We can now apply this to our buffer class. So we have our concept of bufferable, and now our concept becomes a set of requirements, a set of attributes, a set of properties that the type T must support. It's worth mentioning at this point that defining what that set of properties is a non-trivial job. This is not a simple thing to do, and it's beyond the scope of this presentation. I suspect we're going to have a lot of very smart people working very hard on this for a long time to come yet. But we have the syntax now. Let's take another example. Here we have a very common idiom in multi-threaded code, the idea of the scope-locked idiom. The idea that I can take some mutual exclusion mechanism and use resource acquisition is initialization to acquire the lock on construction and ensure that the lock is released however we leave a function. So I've created a very, very simple scope lock class here that does exactly that. We can see here that whatever our type T is, it's very important that it supports two properties. It must support the member functions lock and unlock, whatever they happen to be and how they are implemented. So I could specify that as a concept. In this particular case, we've specified the concept on a particular instance. Please note the compiler doesn't actually instantiate an object at this case, it just uses that for determining these properties. In this case, whatever the type T is must support the functions lock and unlock. We can now use that as a requirement on the template class. Yeah. So let's put that into operation. Here we go, there's a class mutex that supports the methods lock and unlock. And I can use the scope lock to create a lock that will lock the mutex and unlock the mutex, no problem at all. I can create a recursive mutex, also supports the methods lock and unlock. Once again, the compiler is happy to instantiate that template. I could, however, want to use a binary semaphore. In this case, my interface is give and take, the classical semaphore interface. In this case, we don't support the methods lock and unlock, and of course, I will now get an error. And the error will occur at point of instantiation of the scope lock, and it will say, I'm sorry, the concept is ill-formed. The template parameter doesn't support lock and unlock. So notice now I get an error in my client code saying you have not supported the facilities that is needed by this template class. This is really useful. The more observant amongst you would have noticed that I have used a template type deduction guide. I could have used it in this particular example. It just so happens that the error messages are a little bit more succinct when I explicitly instantiate the templates, but I do still get the same effect. I just wanted to keep the error messages a little bit more readable in this case. Where it starts to get really powerful now is I can use concepts instead of template parameters. So in this particular case, I have rewritten my scope lock. So instead of specifying a type name, I am actually specifying a concept. What this means is it's the same as we had before. It's a requirement that says whatever T is, it must support the requirements of the concept lockable. So this is in many ways just syntactic sugar around the previous example. Even better, we can actually use the concept as a supposed normal function parameter. So I have three versions of the lock function here. The top version uses the requires syntax. The middle version uses the concept instead of type name. The bottom version is syntactic sugar again and uses the concept instead of any template parameter. All of these function declarations are equivalent to each other. The advantage of, in this case, the bottom one is it now starts to hide away the potentially horrible syntax of template functions that puts off a lot of beginners. What this allows us to do is actually create much more expressive interfaces for our code. So previously we've got a function here called process any. It takes a template parameter of type T, and we can pretty much call it with anything we want. It will deduce what the type of the parameter is. Of course, whether it works or not depends on whatever the characteristics of the argument are. And of course, if we do get errors, the errors will occur inside the body of the process any function. That's what we had previously. Our second option is we can say this function now called process sum can take any parameter as long as that parameter supports the concept of lockability. That is, it supports the methods lock and unlock. In this case, the semaphore object will fail because it doesn't support lock and unlock. And then if we want to be really explicit, we can explicitly specify that we want it to be a mutex or some subtype of a mutex. So I can now express an interface much more flexibly and saying I either want a specific type, or I want any type at all, a generic type, or something that fulfills some particular category. And that's a really powerful concept. Even more powerful is the idea that concept can be used to specify types. So until C++20, we had two options. We could either specify an explicit type. In our case, it's a mutex. Or we could just let the compiler work it out using the template type deduction rules and use automatic type deduction. For a lot of people that are new to C++ or come from a high integrity background, the idea of automatic type deduction always left a bad smell. This idea of I don't care about the type just feels like bad practice in programming. The idea of having a concept as a type now says, I really don't care about the specific type, I just care about its characteristics. As long as it supports the characteristics I'm interested in, then I'm not really interested in its specific type. Now that is much more important, I think, in programming and much more flexible. This leaves us with one final question. If I've got functions that are overloaded, in this case I've got the process function, one overloaded for the concept of equality comparable and one overloaded for the concept of value comparable, which one does the compiler use? You'll notice in this particular case that value comparable concept is a superset of equality comparable. That is, a valuable comparable type does everything that an equality comparable type does, but can do more. In this particular case, I've supplied a call to the process function with two integers. Well, of course, integers support both the idea of equality comparison and value comparison. So the compiler could potentially call both of those functions. In this particular case, the compiler will always pick the most restrictive concept in this case. So in this case, it will pick the value comparable one. That's somewhat easier to see if we take user-defined type. So here we have a waypoint represents a place as part of a navigation system. It makes sense to compare waypoints for equality. Are they the same place? It doesn't make sense to compare them for value. Is one place greater or less than another place? That makes no sense. Of course, in this case, if I call process, the waypoint only supports equality comparison, so I'm always going to get the equality comparable version. If I take a different type, like a pressure type, it makes sense to compare those for equality or inequality. And of course, I can specify whether one pressure is higher or lower than another. Then in this particular case, the compiler will pick the more restrictive concept, which in this case is value comparable. In this particular case, please note again, these value comparable and equality comparable concepts, these are gross simplifications for the point of this exercise. In actual fact, there are a lot of subtleties around defining concepts. And I think that is going to be the thing going forward here. What do we take away from this then? Generic code. The idea of generic code is don't repeat yourself. If the algorithm is the same for all types, it makes sense to make it a template function so we can reuse that code. Let the compiler generate the various versions of functions that we need, but it doesn't always work. Generic code will always impose some sort of requirement on the template parameter. The problem with that is that quite often the first time we find out that we've got something wrong is deep in the body of the generic code, which may be code that we haven't written, which makes debugging a real challenge. Now we have mechanisms like substitution. Failure is not an error that can give us mechanisms to enable and disable functions, but they are syntactically challenging, shall we say. This new introduction of requirements and concepts into the language does a couple of things. First of all, it allows us to specify templates much more expressively, but also, and probably from a day-to-day use, means that the error messages generated by generic code are far more palatable to normal humans. And I think this going forward has the potential to really change the way we look at generic code in C++, particularly in the way we can now use syntactic sugar to use concepts to specify generic code and also generic objects as well. I think we have the potential to really restructure the way C++ is going forward from this point. I think it's going to be very interesting to see where the language and where the user community takes it. So I think that is a good place for me to stop talking. So thank you very much for your attention. Hope that was a useful introduction. You can now start looking at these things and reading some of the more sophisticated examples and start trying this out for yourself in your code. And with that, I'll say thank you again. If you're interested in reading this up in a bit more detail, go onto our blog, blog.feabhas.com. Search for concepts. I've written all this material up as a full blog article, so you can read it after the class as well.